if I have, whoops, hold on a second. I gotta take a snapshot of this. If I have a sine curve, inverse functions are always, 100% of the time, the reflection over that line. The only thing is that in order for that function, sine of x, to have an inverse, it has to be 1-to-1. And notice that it does not pass the horizontal line test, right? In other words, I can't draw a horizontal line through that sine function. So the sine itself does not have an inverse unless you do one very important thing, which is to restrict the domain. So the way they do that is to restrict the domain between minus pi over 2 and pi over 2. So really what we're looking at is this part of the curve only. And the way we're going to get that inverse is to reflect it over the line. All inverses are reflections over the line y equal x. That's what that line is, y equal x, the dotted line. So if I take the green part of my line, in other words, I've restricted the domain of the sine function such that it's now 1-to-1. Notice that the green part only passes the vertical line test and it passes the horizontal line test. So what the inverse looks like is that. And that's basically graphically what inverse trig functions are. Practically, it's much easier to understand. I should have started with this. If the sine of 30 degrees equals 1/2, which it does, that means the inverse sine of 1/2 equals 30 degrees. In other words, we take trig functions of angles to get ratios, but we take inverse trig functions of ratios to get angles. And notice that my domain and range are just perfectly switched here. And that's a key part when you get into the calculus of these trig functions, is knowing that with the inverse function, the domain and the range just switch. You with me?
Yep.
Okay. So we've got some stuff to memorize here, which are the derivative formulas for sine, tangent, and secant. Now, this is a little bit like memorizing the derivative formulas for sine, tangent, and secant. Notice that when I taught you how to memorize those, I picked these three functions, right? And then we knew what the cofunctions were. But the ones you have to memorize are sine, tangent, and secant, whether we're talking about the trig functions or the inverse trig functions. And the relationship to their cofunctions is also significant. So let's talk about what the derivative of inverse sine of x is. Oddly enough, when we take derivatives of inverse sines, we get polynomials. We get 1 over square root of 1 minus x squared. if we look at, here, let me erase some of this stuff so I don't fill up my page with the stuff that we don't really need. I'm going to draw a table just like I drew a table when we were doing derivatives of trig functions. The tangent inverse is 1 over 1 plus x squared, and the secant inverse, these are the derivatives. This is the function here, and this is the derivative in this column. And the secant is 1 over absolute value of x times the derivative of x squared minus 1. Now, this might look impossible to memorize, but it's not really. The easiest one to memorize is the tangent, because there's no radical sign. It's just 1 over 1 plus x squared. The sine is similar, only it's 1 minus x squared under a radical sign in the denominator. And the secant is similar, only the x squared minus 1, the x squared and the 1 are reversed for secant relative to sine, and there's an absolute value of x in front. Okay? Now, when I said they're related to their cofunctions, the inverse cosine is just the negative of that. It's negative 1 over the square root of 1 minus x squared. The inverse tangent is the negative of this. So it's minus 1 over 1 plus x squared. And the inverse, or rather the inverse cosecant, is the negative of the secant. So it's minus 1 over all of that. And remember that reasoning when we were doing derivatives? As long as you could memorize the derivative of sine, tangent, and secant, then you could always figure out the derivative of cosine, the cofunction of sine, cotangent, the cofunction of tangent, and cosecant, the cofunction of secant. But you've got to memorize these three. In both cases, whether you're talking about memorizing the derivatives of the trig function, or whether you're talking about memorizing the derivatives of the inverse trig function. Now, do you have the calculus book?
No.
Calculus book?
Not on me, but I can go grab it if you want.
Well, on my calculus book, the inside cover has all of these derivatives of these trig functions and integrals. So until you memorize it, it's a great thing to have for reference. You don't have to look to a certain page in the book to find these formulas. They're all on the inside cover, but I don't know if that's true with your book or not. I'm not sure we have the same book. I've got Calculus of a Single Variable by Larson, Hostetler, and Edwards. I believe that's the one they use.
I don't have that one. I have a different one.
You have a different one? And does if you can lay your hands on it quickly, go ahead, because I wouldn't be surprised if you have a table of derivatives and integrals on your...
I definitely don't have that in like the first cover, but I don't know for like a fact that we have like all the information like that like near the back of the book.
Okay. Well, until you memorize it, you need a place that you can lay your hands on it easily.
So do you think I should go grab it then?
Well, yeah, I would grab it, and let's find the page that this stuff is on.
Okay.
Because you're going to need to refer to it, that page, until you memorize this stuff.
Okay. All right, I got it.
Okay, I'm going to erase the cofunctions. We don't need to memorize the cofunctions yet, and there's really nothing to memorize with the cofunctions. It's just the negative of the function.
Uh-huh.
Okay, so these are the three we need. And this is the answer to problem 1. State the derivative formulas for these three. Well, this is what they are. Now, let's talk about the chain rule. In other words, the very first question is number 7, where they want you to take the derivative of inverse sine of 2x. Well, that means, and really the way you should do these is using u substitution. So you see number 7 down here?
Yeah.
Okay, so if we're going to take the derivative of the inverse sine of 2x, then we're going to use u substitution. U is going to be equal to 2x. Okay? And if we change that to a u instead of an x, then the only difference is that's the derivative of the outside, but we have to multiply it by the derivative of the inside. So the table you're looking at probably has that. Am I correct? It's the end.
Yeah, I don't have that in my table. It just says algebra and trigonometry stuff.
So you don't have a table of these inverse functions?
No. I'll go look for it though.
Well, look in the, yeah. Well, I don't want to spend the whole session you looking for the table. I can give you the information.
Okay.
Let's just work off of that. Okay?
Okay.
In fact, let me erase the tangent, and we're going to work off of just the sine for the moment. Because they give you 7 or 5 questions here that are just derivatives of inverse sine. Now, the reason I switched x for u is in case it's not x, in case it's something more complicated than x. For example, number 7 is 2x. Okay? So, tell me what the derivative of, in other words, number 7, what is f prime of x? Plug it directly in. So what's the derivative of the outside? Meaning, what's the derivative of sine of u? The inverse sine of u.
The inverse sine of u would be 1 over
Follow the formula that you're looking at on my screen.
1 minus,
U squared
yeah.
times u prime. Well, what's u prime? What's the derivative of u?
2u.
Just 2. If u is 2x, then the inside is 2x. And in other words, all we're doing is applying the chain rule. Okay? That's the derivative of the outside. That's the derivative of the inside. We go back and we substitute for u what it's actually equal, which is 2x. And so now we have 2x in parentheses squared. And there's our answer. Now I can simplify that a little bit. That becomes 2 over the square root of 1 minus 4x squared. So that's the answer to number 7. Okay? Let's do a few more and you'll get the hang of it. I like the way they do all sine and cosine. So number 8. this is going to require you to use the product rule. And there's no inside here. In other words, for number 8, we're going to use this formula. Hold on. I want to be real clear about this because I want you to understand this. In other words, when the inside is just x, then this is the formula for the derivative. It's 1 over the square root of 1 minus x squared. If the inside is something other than x, then you have to multiply it by the derivative of that inside. Okay? But for number 8, we're going to use the product rule. So what's f prime of x going to be equal to?
It'll be so it'll be x.
If you're thinking more than 3 seconds, you're not starting this problem correctly. Always start with that. That's the first thing you want to write, always. When you're using the product rule, is the first function. And the first function in this product rule is x. Now we're going to multiply that by the derivative of the inverse sine. What's that?
It'll be 1 over x squared. No, 1 minus.
You need the radical sign.
X squared.
Okay. That's the first half of the product rule. Now do the reverse of it for the second.
1 times sine -1 x.
So there's our answer, and I can put that x there. So you get x over square root of 1 minus x squared plus inverse sine of x. That's the answer to 8. Okay? As long as I have the formula up there and we can read 9, let's do 9. Whoops, hold on. In other words, for the moment, I don't mind you reading off the formula just until you get the pattern. Let me erase that too. Okay? So, number 9 looks really complicated, but it's not. You're going to have to use the chain rule twice. So let's talk about the derivative of the outside.
That would be 1 over.
Oh, the outside is cosine of something. In other words, that's u. So what's the derivative of cosine of u?
Oh, so it would be the outside would be sine.
Minus sine.
Yeah.
Derivative of cosine is minus sine. The inside doesn't change. In other words, u. So that's the derivative of the outside. Now I have to take the derivative of the inside. Well, the inside is u. It's whatever's in the parentheses, right? Okay, what's the derivative of what's in the parentheses?
So that would be 1 over the square root of 1 minus 2w squared.
And make sure you put that 2w in parentheses because it's the whole thing that's squared. In other words, that's going to end up being 4w squared.
Okay.
Okay. Now, there was a further inside. In other words, our first inside was that. But there's also an inside to the inverse sine function, 2w. So I have to multiply everything by the derivative of that inside.
I thought it just wouldn't matter.
No, it matters. You got to multiply it by 2 because the derivative of that second inside is 2. And this is the reason that we don't work inside out. In other words, we've talked about it before. I don't know why the chain rule doesn't read derivative of the inside times the derivative of the outside. And it's when you have more than one inside, it works better if you start with the derivative of the outside times the derivative of the inside times the derivative of that inside. And you can go as many chains as they give you. There could be 4 chains in a function. You just have to take them one at a time. Okay, let's look at number 10.
So first off, you put it, there'd be the first inside, which is, no, you do the outside, so it's 1.
On number 10, there's only one inside, and it's natural log of x. In other words, what I really have here.
Wait, why is x then not another inside?
Well, because it's x. If it was natural log of 2x, then it would be another inside. But if the inside is x, you don't need to treat it as an inside because the derivative of it is 1.
But technically it is another inside.
I suppose. Not really, but not really. Not by the way we think of insides. In other words, if the inside is x, then it's not an inside. Any more than I say the derivative of sine x is cosine x. Well, x is not the inside because it's x. But if I say the derivative of sine of 2x is cosine of 2x times 2, my inside is 2x. Okay? But on number 10, we do have an inside. It's natural log of x. And we only have one inside.
Okay.
So let's take the derivative of the outside. What is it?
So it would be 1 over the square root of 1 minus natural log of x squared.
That's the derivative of the outside.
Then the inside is,
The inside is u prime. What is u prime if u equals natural log of x?
It's just 1 over x.
So that's the derivative of the outside. And there's your answer. With me?
Yep.
Okay, good. We're gonna go and do number 11 and 12, and without me having the formula up there. See how well you memorized it. So give me the formula. What is if y is inverse sine of u, what is y prime?
It would be 1 over the square root of 1 minus u squared
times u prime, the derivative of the inside. And this is why when they give you a page of formulas, this is the one you're going to see on it. In other words, they're always going to assume that there's an inside. Notice on questions 13 through 30, every single one has an inside. Nothing is just x.
Mm-hmm.
They didn't ask us for the inverse tangent of x. There's no inside there. But everything else, u is whatever's in the parentheses, or in the cotangent case, u is square root of z. Okay? So this really is the formula you're remembering, but what it really is 1 over the square root of 1 minus u squared times u prime. That's the derivative of the outside, that's the derivative of the inside. Okay, so number 11, back to just sines. Let's focus on sines since we maybe have that memorized. So get me started. What's the derivative of the outside?
The outside for 10 or 11? 11. So it would be 1 over the square root of 1 minus e to the negative 4x.
Okay. I was going to write it like this just to be clear about what we're doing. And that is e to the minus 4x times what?
And that would be times just e to the minus 2x.
Okay, that's not the derivative of e to the minus 2x though.
What is it then?
That's still has another inside. In other words, there's our second inside.
How would you compute that inside?
Derivative of that.
And then would you just multiply it all by negative 2 then?
Exactly.
Okay.
So times negative 2.
But if it has nothing in front of it, then it's not really relevant.
Well, if it was minus x, it would have to be times minus 1.
Okay, so no matter what, you always take the inside. But
x, then there's no second inside. If it's just e to the x.
Yeah, okay.
So, yeah, our final answer looks like 1 over square root of 1 minus e to the minus 4x times 2e to the minus 2x. And there's no simplifying that.
Yeah, that's okay.
Only thing to remember is that all of these look like they have multiple insides. Let's do 12.
12. So you start off with 1 over e sine to the x.
Hold on. Remember that 2 of these things have radical signs in the denominator. The only one that does not is tangent. Tangent is very simple, 1 over 1 plus x squared. So the inverse tan, the derivative of the inverse tan is that. And that's the easiest one to memorize, is the inverse tan. Okay? But we're still doing sine. So we'll get to the tan next problem.
Okay, so it's 1 minus e sine 2x.
And the best way to write that probably is, for the moment, like that.
Yeah.
Okay. Times what?
And that would be times,
I'm going to write it to the right just so we're clear that first thing is the derivative of the outside. Now what's the derivative of e to the sine x?
It would be cosine e to the x.
No? Well, let's start with the derivative of e to the sine x. What's the derivative of the outside of that?
It would be cosine.
It's e to the sine x. Now we have a second inside that is sine x. So we have to multiply this whole thing by the derivative of our second inside. And that is cosine x, like you kept wanting to do. It's just that I wanted you to do it in order. Okay? So we had 2 applications of the chain rule. That was the derivative of the outside. That was the derivative of the first inside, but it's really the outside. In other words, the way to look at this, Jake, is if I had e to the sine x and I said find the derivative of that, Well, you'd say y prime equals what?
I'd say the y prime is cosine x e to the cosine x.
Okay, but you're doing the inside first. Just try to bear with me and do it in the order that I'm thinking so that I can tell whether you're doing it right. In other words, what's the derivative of the outside?
It's cosine x.
No. You're not using the power rule. You're using the principle that if I have e to the u, the derivative is e to the u times u prime.
Yeah, isn't that what it is?
Well, you keep starting off with cosine.
Well, I'm just finishing it in the simplified version.
Well, please don't do that, because I don't know what you're doing when you do that. In other words, what it looks to me like you're doing is you're starting with the derivative of the inside first.
Okay.
If you start with the derivative of the outside, I got to make sure you understand what I'm talking about here. So I've got to be able to follow your reasoning. Now times the derivative of that inside. So for this problem here, there's only one inside. It's really easy to do. But when e to the sine x is the first inside by itself, which it is in this problem, then you have two insides. So you have to treat it as just two applications of the chain rule. You'll get it. Here, let's try tangent. Now, I'm going to write the tangent up there as being 1 over, and I'm going to put an x in case there's no inside. So that's the inverse tangent. That's the function. That's the derivative. Okay? So what's 13 going to be?
That'll be 1 over 1 plus 10x squared.
Which is 100x squared. Okay. Times the derivative of the inside.
Which would be just 10.
Okay. Let's try 14. Now, first of all, tell me what the derivative of inverse cotangent is.
You just put a negative sign in front of the tangent.
Okay. So we're going to know how to do this problem then. In other words, there's nothing we don't know how to do with this problem.
Mm-hmm.
Even though it's going to be complicated because we're going to have to use the product rule, and then we're going to have to use the chain rule because there is an inside.
Yeah.
So start with the first part of the product rule.
So the first part of the product rule would be
remember if I said you have to wait, if you're waiting more than 3 seconds, you're doing it wrong.
Well, yeah, I know, it's just x.
Okay, that's always the way to start out. Then figure out what the derivative of the second part is. But there should be no thinking involved on the first part. It's u. If you're taking the derivative of uv, the first part is u times v prime plus u prime v. At least with me. I realize you can write it in either order, but being able to write it in either order doesn't do you any favors. All it does is it complicates it. Every single student I get that can do it in either order, they start looking as to which one they can figure out first. And so they always start with that one. And that's not the way to do these. The way to do these is to always start with that first function, take the derivative of the second. So what's the derivative of inverse cotangent?
It's 1 over
minus 1?
Yeah. Over 1 plus x divided by 3 squared.
Okay. Times the derivative of the inside.
Which is just 1/3.
Okay. Now that's just the first part of the product rule, right? In other words, what that is u, and that's v prime. You with me?
Yep.
Okay. Now what's the second part?
Then it's cotangent -1 times x divided by 3.
Okay. Let's talk about terminology for a little bit. That's not really the correct terminology. It's, first of all, it's not cotangent -1 times x over 3. It's the inverse cotangent, or you could call that the arc cotangent. Either one. But you don't want to call it cotangent -1. Okay? You don't. And it's like sine notation. When you say sine of x, it's not sine times x, it's sine of x. This is the inverse cotangent of x over 3. And that's your answer. Okay? Let's do 15.
So that would be
15 all on your own here.
1 over 1 plus 2y minus 4 squared.
And the only thing, always put that in parentheses. Okay, now what?
Then you want to multiply by the inside, so it would be 4y, just times 4y.
And I put that in the numerator rather than as multiplying it by something else. Because your table, if I had tangent, inverse tangent of u instead of x, well, the derivative of that is u prime, that's the derivative of the inside, times 1 plus u squared, or all over 1 plus u squared, which is the derivative of the outside. Okay? So this is the way you're going to see it in any table that has these formulas. Is they're going to assume that you're looking at a composite function. In other words, that u is something other than x. Notice that if u were x, well, the derivative of u is 1, so it still works. Even if x is the inside, you could make the argument that there's always an inside. Sometimes it's x, sometimes it's something else. So in a way, you weren't wrong when you were making your argument, okay? So I think you've got tangent down, and I think you've got sine down, and you've got cotangent down, and you got cosine down. The one we haven't done yet is cosecant. Now, oh no, we haven't done secant. Let's not skip any further than we have to here. I think you know how to do 16, am I correct?
Yeah, that's pretty simple.
And I think you know how to do 17.
Yep.
The inside is square root of z. Okay, let's do 18. Let me erase this so that I can replace it with the secant. So the inverse secant, and this is probably the hardest one to remember, especially when I write it like that, instead of the -1. So I'm going to do the inverse secant of x. What's its derivative?
What?
What is its derivative?
I have no idea.
Okay, it's close to sine. There's a radical sign. Remember sine was 1 minus x squared? Well, secant is x squared minus 1. But there's also the absolute value of x in front. So that's the derivative of inverse secant. Okay, let's do this one, 18. Hold on.
Okay. So it would first off be
Derivative of the outside, yeah.
Yeah, so it'd be 1 over the square root of x, because it's unchanged.
Absolute value of square root of x. Now, are you saying you don't need the absolute value sign there because it's square root and it has to be positive?
Yeah.
Okay, that's fair. But the formula, notice you do need the absolute value. It's just in this case, I happen to know that square root of x is always positive. There's no value for x where that can be negative. So I don't need the absolute value sign. But what's the rest of it?
Times the square root of the square root of, no, I guess, no, it's just renders it obsolete. So it'd just be x minus 1.
Okay, that's the derivative of the outside. Now what's the derivative of the inside is x to the 1/2. So what's the derivative of the inside?
So it'd be 1/2 x negative 1/2
Okay.
to the negative 1/2 power.
Yeah. Now, notice that I can do some heavy simplification here. In other words, that x to the minus 1/2 means it goes in the denominator and it's the square root of x, right? So I've got a square root of x times a square root of x. So my final answer, I've got this 2 that's in the denominator. That x to the minus 1/2 times this square root of x gives me an x times x minus 1.
Yeah.
And I think that is your answer. Okay. Let's do one more. Let's see if we can do one more secant, if we can find a secant. Yeah, let's do 25 next.
Okay.
I have the formula written up there. So, the derivative of the outside. Doing 25.
So it would be 1 over the absolute value of the natural log of x.
And here we do need the absolute value sign because natural log of x can be negative. Keep going.
So square root of the natural log of x squared.
And again, without the parentheses, that means something different. Without the parentheses, that's natural log of x squared. With the parentheses, that's natural log squared of x. It's kind of similar to sines and cosines. In other words, whether that 2 is between the natural log and the x or it's to the right of the x matters. This one is the same as natural log. That's what that means, what we've written. That means natural log times natural log, which is natural log squared of x. Okay, and the rest of it?
And then minus 1.
Okay.
To multiply it by the 1 over x.
There you go.
And I don't think you can simplify it anymore.
No. I don't think so either. No. Every now and then you'll get something inside the radical sign that can be simplified because you can pull it out. In other words, usually it's numbers and variables to powers, but a lot of times you can pull some of that outside, and you would be able to simplify it, but not this one. Okay, so we've done the three primary ones. Now let's do 20. I'm just looking for ones that look interesting.
Okay, so first off, it's going to be
the derivative outside.
It'll be 2 cosine, 2 arc cosine t.
Good.
Times times -1 over the square root of t. One minus t squared.
Perfect. Exactly. And the thing to remember about cosine is that it's the opposite of secant. Where its cosine is 1 minus x squared, secant is x squared minus 1 inside the radical. And tangent is just 1 plus x squared without a radical. So there is a pattern to the three primary ones that allows you to at least relate one to another. In other words, if I have the secant one written up there, you should be able to remember what the cosine one is. All right, how about this one, 22?
So first you're going to take the natural log. So it's going to be 1 over arc tangent t. And then you're going to multiply it by 1 over 1 plus t squared.
See, you're halfway to memorizing all 6 of these. Exactly, and that's the answer. Now, 28 looks like a good one. Notice that there are at least 2 insides. That is the first inside I'm going to come across. That is the second inside I'm going to come across. Okay. So the first thing to do is the derivative of the outside.
So that would be cosine times arctangent times of natural log x.
Okay.
And then the second, so you're going to multiply that by 1 over 1 plus natural log x squared.
Well, I'm going to write it like that.
Okay, yeah.
Okay.
And then you're going to multiply it again by 1 over x.
Very good. I think you got this chain rule down. Don't you?
Yeah, I do.
Okay. Now, the other big topic that you sent me was derivatives of the inverse function. And let's talk about that for a minute, because that also has to be memorized. And there's a good way to memorize it. First of all, if f and g are inverses of one another, then we know that f of g of x is equal to what? by definition of inverse?
Uh,
When you take a function of its inverse, it's always equal to x. And likewise, g of f of x would also be equal to x. That's how you can prove that two functions are inverses of one another, is test it. In other words, make sure that f of the inverse is equal to x. If it isn't, then they're not inverses of one another. Now, differentiate both sides. What do you get?
f prime of x and g prime of x.
Hold on. You get f prime of g of x. That's the derivative of the outside.
Times g prime of x.
That's the derivative of the inside. And that's just the left side of the equation. What's the right side?
1.
Okay. Now, the question you're always going to be asked for is to solve the derivative of the inverse. In other words, they're not going to give you the inverse function. They're going to give you the function, but they're going to want the derivative of the inverse function. It's another little game they play. So the derivative of the inside is going to be 1 over the derivative of the outside. You see how I got that just by algebra?
Mm-hmm.
In other words, I go from here to here. Okay? And this is what you have to memorize. But you don't have to memorize it if you can work it out. In other words, I can always work it out because I always know that the derivative, or excuse me, composite function where I have f of its inverse, I know it's equal to x. And then I just differentiate both sides, I end up with this formula here down on the lower left. Now, I'm going to give you an example problem just to show you how this works. This is very difficult to get. So first of all, remember that g is the inverse of x. So we'll write our formula down here. All right. Now, perfect example is the following one. And we got just enough time for me to explain this example for you. And then the next time we meet, we'll do a bunch of these. And these are a lot tougher. And what's tough about, well, they're not so much tough if you know one thing. Question is, what is g of x? In other words, that formula is going to require me to know g of x when x is 3. And this is the tough part. In other words, what is g of 3? Well, here's the thing. We know g is the inverse of x, of f, correct?
Yeah.
So when x is 2, f of x is 3. In other words, f of 2 equals 3. If you plug in the numbers, you get 8/4 2 plus 2 minus 1. So that's a true statement, correct?
Yep.
Well, here's the part that's hard. That means that g of 3 equals 2. Inverses have, you swap the domain and you swap the range. So in the f function, my domain is 2, my range is 3. In the g function, my domain is 3, my answer is 2. So knowing this relationship is the key to doing all these other problems. Now we can solve what g prime of x is. Let's try it. G prime of x, actually, let's say g prime of 3, because that's what they want. What is g prime of 3? Well, plug it into the formula. It's 1 over f prime and g of 3. With me? That's all I did was plug it into the formula. Now, I happen to know what g of 3 is because I knew what f of 2 was. So g of 3 is 2. So this is 1 over f prime of 2. Now this is a little confusing, don't worry about it. I'm just giving you this one example to end tonight's session, and then we're going to go over this all again next time. But the critical thing is this part right there. Okay, now f prime of 2 is pretty easy, right? So all I got to do is take the derivative of f, substitute 2. In other words, what's the derivative of f? It's 3/4 x squared plus 1. When I substitute 2 for x, I get 3 plus 1. So f prime of 2 is 4. So that's my answer, 1/4 for g prime of 3. And in case you haven't figured it out, this is not obvious at all. What they're asking you to do is they give you a function, and first of all, we don't even know how to figure out the inverse of that function. Notice that, remember how you figure out inverses. You swap the variables and solve for y. Well, if I got y cubed and another y, I got no idea how to solve for y. So I don't know how to solve for the inverse. I don't need to. That's the beauty of this. That's the magic of this. I don't need to figure out what the inverse function is. Not as long as I have this formula. And not as long as I can figure out where the original function is equal to 3. And I can do that. In other words, the first thing I have to do is set that equal to 3 and solve for x. Turns out that x is 2. So I can make the statement that f of 2 equals 3, which allows me to make the statement that g of 3 equals 2. That allows me to answer the problem without ever knowing the inverse function.
Okay.
And we definitely need a session working on those. And you've got a whole page of them that you've sent, and it'll take a full session to do 5 of them, I'm guessing. Okay. But, and this is fairly, yeah, you'll notice that this last page here, 59 through 66, derivatives of inverse functions. In fact, 51, 52, this is all going to be similar stuff. We'll get to that next time.
Okay.
Okay? All right, Jake. This is Thursday. I'll talk to you Tuesday.
Sounds good, man. I'll see you later.